Good morning, good afternoon, and good evening, everyone. In this video, me and my classmate Lopez will explain the different methods of evaluating limits and the concept of continuity. First, let me define some important symbols. The symbol lim means limit. It tells us we are finding the value that a function approaches. If we write x pointed out to positive 2, it means x is getting closer and closer to 2. If we write x pointed out to negative 2, it means x approaches the left side. If we write x pointed out to positive 2, it means x approaches the right side. This symbol right here means infinity, which represents values increasing without bound. And the symbols right here means negative infinity. Now let's start evaluating limits. Limit as x approaches 2 of 3x plus 4. Since this is a polynomial and it is continuous, we can substitute directly. Replace x with 2. Three 2 plus 4 equals 6 plus 4 equals 10. Final answer is 10. Direct substitution works when there is no indeterminate form like 0 over 0. Limit as x approaches 3 of x squared minus 9 over x minus 3. If we substitute 3 directly, we'd get 9 minus 9 over 0, which is 0 over 0. This is called an indeterminate form, meaning we must simplify first. We factor the numerator x squared minus 9 equals to x minus 3, x plus 3. Now cancel x minus 3. We are left with x plus 3. Now substitute 3. So we get 3 plus 3 equals 6. The final answer is 6. Factoring removes the removable discontinuity. Limit as x approaches 4 of squared x minus 2 over x minus 4. Substituting gives 0 over 0 again, so we multiply by the conjugate. Which is turns by x squared plus 2 over x squared plus 2. The numerator becomes x minus 4. Now we cancel x minus 4. We get 1 over x squared plus 2. Now substitute 4 equals to 1 over 2 plus 2 equals to 1 over 4. Final answer is 1 over 4. Conjunction helps eliminate square roots and indeterminate forms. For a limit to exist, the left-hand limit must equal the right-hand limit. Given the piecewise function, as you can see over here, find the limit as x approaches 2. Left-hand limit. 2 plus 1 equals to 3. Right-hand limit is 3. Since both are equal to 3, the limit exists. The final answer is 3. As for another example for positive infinity, which is from right-hand infinite, limit as x approaches 0 from right of 1 over x. As x gets closer to 0 from the positive side, the denominator becomes very small positive. The value becomes very large positive. The final answer is positive infinity. As for another example of negative infinity, which is the left-hand infinite, limit as x approaches 0 from left of 1 over x. Now the denominator is very small negative. The value becomes very large negative. The final answer is negative infinity. This shows a vertical asymptote at x equals 0.
Lesson 3. Transcendental functions. Transcendental functions include exponential, logarithmic, and trigonometric functions. Example 8. Exponential function. Limit as x approaches 0 of substitute directly. E equals 1. Final answer is 1. Exponential functions are continuous everywhere. Example 9. Logarithmic function. Limit as x approaches 1 of in x. In 1 equals 0. Final answer is 0. Logarithmic functions are continuous for x greater than 0. Example 10. Special trigonometric limit. Limit as x approaches 0 of sin x over x. This is a special limit identity. Final answer is 1. This identity is very important in calculus. Lesson 4. Continuity. A function is continuous at x equals 0 if f of a exists. The limit as x approaches a exists. The limit equals f of a. If any of these conditions fail, the function is discontinuous. Example 11. Continuous function f of x equals x squared. At x equals 2, f of 2 is 4. Limit is also 4. Since all conditions are satisfied, the function is continuous. Example 12. Last example. Discontinuous function f of x is equal to 1 over x. At x is equal 0. The function is undefined. The limit does not exist. Therefore, it is discontinuous at x equals 0. In conclusion, limits help us understand how a function behaves near a specific value. Continuity tells us whether the function has breaks, jumps, or holes. These concepts are essential foundations in calculus and are important for understanding derivatives and advanced topics. Thank you for watching.